Hi everyone, I am Dhruv Sharma, and on behalf of my collaborators Ali Hussain Kuwajarwala and Professor Florence Kurti, I am honored to present our work on augmenting imitation experience via equivariant representations. The motivation behind our work is that visual navigation policies learned via behavioral cloning often perform poorly under covariate shift. To partially address this problem, data from additional sensors, that is, observation action pairs, are collected from additional sensors, and this additional information is used to augment the training policy. For example, in their paper End-to-End Learning for Self-Driving Cars, NVIDIA showcased this on real self-driving cars, where they used data from additional two cameras, that is, a left and a right camera, and augmented their driving policies. However, dealing with additional sensors can be expensive and resource intensive. So, can we make visual navigation using a single camera more robust? One way to do that is try and predict viewpoints from different cameras in the latent space. And to do that, we can use the concept of image equivariance. Image equivariance is defined as follows. The image features are said to be equivariant to a transformation applied to the input image if they change predictably in the feature space. Mathematically speaking, and to make it more clear, for a transformation G applied to the input image I in the pixel space, there must exist a corresponding transformation Mg that would approximate the embedding for the image G of I. In other words, image features behave in a predictable way as a function of transformation applied to the input image. This is what our systems looks like. Step one is to learn features that are equivariant with respect to different camera viewpoints. Step number two is to use these learned features to augment the training dataset for a behavioral cloning policy. And step number three is to train a vision-based navigation policy using this augmented dataset and imitation learning. To learn the equivariant features, we use an encoder-decoder network. The equivariant map MIJ is modeled as a fully connected network. To know the details of the training process, we request you to read our paper. The experimental process is as follows. We collect data and use this data to learn equivariant features as covered in the last slide. Further, we use these learned equivariant features to learn control via imitation learning. To assess and evaluate our method, we train and compare three different policies. Policy number one is trained using data collected from a single camera. Policy number two is trained using data collected from multiple cameras. And policy number three is trained using data collected from a single camera plus our equivariant augmentations. Our experimental process includes experiments in simulation as well as experiments on real robot. The simulation experiments include experiments on a flying vehicle as well as a ground vehicle. The simulation results showcase that our method using equivariant augmentations performs better than using a single camera and is more robust. For real robot experiments, we use a ClearPath Husky equipped with three forward-facing cameras. We use this ClearPath robot on a 600-meter long test path on a trail at the University of Toronto Mississauga campus. Our results and experiments showcase that using a single camera with our equivariant augmentation produce similar performance when using multiple cameras. To conclude, we use the concept of image equivariance to augment our training policies and to train more robust control policies for visual navigation. Thank you for listening.